In this module, we are going to talk about EIGRP metrics, the composite metric, and some of the other metrics that EIGRP might use in some circumstances, and the best path selection process in EIGRP. But this is not going to be so simple and straightforward as you might expect. We are first going to talk about routing information exchange, or how do EIGRP routers actually exchange the information about the routing tables. What are the EIGRP metrics? What are the components? How is the final metric that is used in the routing table calculated and determined? Then we are going to examine what are the internal databases in use by EIGRP, and here we are going to look at the topology database and obviously the best path selection process that happens there. And obviously here we are going to look at how the certain router locally makes this determination, what is the best route, and if it cannot make a local determination about the best route, how it might ask other devices in the network about what the best path to reach certain destination is. And finally, we are going to talk about equal and unequal cost load sharing as supported by EIGRP. EIGRP routing information exchange is a process that begins as soon as neighbors have discovered each other and they have some routes that they need to communicate to each other. This process is accomplished and completed using separate packets, separate type of EIGRP packets called update and acknowledgement packets. Now, I should really point out that treating the acknowledgement packet as a separate packet type is really just a minor logical concept, because the acknowledgement packets are really just unicast hello messages that are sent by the recipient of the information to the sender of the information. But let's take one step back. The update packet is a separate packet type, and it contains information about the routes that EIGRP router needs to communicate to its neighbor. Once this information has been compiled, once the router knows what it's going to tell its neighbors, it's going to send this update information, it's going to send the route to the neighbor, and it's going to expect the acknowledgement of this packet. As I say, this acknowledgement comes in a form of a unicast hello. But what about the actual update? Is the update unicast or is it multicast? That depends on the interface type on which you have this configured. If the interface type that you are using is, for example, Ethernet that supports multiple neighbors, the actual update packet will be sent to 224.0.0.10, which is the multicast destination used by pretty much all EIGRP communications, and then every single neighbor will need to acknowledge this packet separately. If we don't get an acknowledgement from a particular neighbor in a certain period of time, non-configurable period of time, in that case, we are going to send a unicast update to that neighbor and expect the response. If we don't get it, we are going to declare that there is something wrong with this neighborship. Now, this operation that I just described is something that EIGRP calls a reliable multicast delivery. This is a process that always happens in EIGRP information exchange, but you as a network engineer, as the end user of the equipment, really have no way to influence how this process happens or modify these timers. These timers are actually dynamically calculated and determined by each individual device. But while I'm on a subject of talking about EIGRP packet types, let me just mention that there are overall 5 packet types if we treat an acknowledgement packet as a separate packet type. They are the hello, the update, the acknowledgement, the query and reply packets. I'm going to talk about the query and reply a little bit later on. But taking even one more step back here, there are 2 kinds of updates that EIGRP can send. This is the full update of routes, and this usually happens when the neighbors have first discovered each other. When this happens, when the neighbors first discover each other on a particular network segment, they are going to exchange all the information about all the routes. The good news about EIGRP is that this really happens only once. There is no periodic information exchange, there is no periodic reflooding of this information. This information is going to be valid as long as the neighbors exist, or one of the neighbors decides that information that it sent previously is no longer valid, and it's going to send a new update. For all the changes that happen after this initial flood of information has happened, after this initial large update has gone out, are simply going to be partial updates when the metrics on particular routes change, or if the new routes have been added or being removed from our routing tables. Let's now take a look at this process in some more detail. So let's say that I had two routers, R1 and R2, that are interconnected on, let's say, their gigabit interface is 1, and that the network between them was 192.168.12.0/24. And let's say that on R1, say, we had a loopback interface 192.168.01/32. So when we configure EIGRP to run between them, and let's say that we are going to configure EIGRP process, let's say 12, to run between them, what we expect to see here is R1 and R2 to send each other periodic hellos. So if I enable my EIGRP only on the gigabit interfaces, the only communication that I'm expecting to see are going to be EIGRP hellos. But let's say that now I add my loopback interface to the EIGRP configuration. What's going to happen is R1 is immediately going to communicate this information to R2. So this is going to be the update message. And once R2 has received and processed this update message, what it's going to do, it's going to send back the acknowledgement to R1. So this is the relevant part that happens here. There is going to be an additional process that's going to happen, and that's going to be that R2 is going to inform R1 that it has this new route, but it's going to send it with an unreachable, infinite metric back to R1, simply telling R1, hey, I have this route, but it's not really reachable through me because I have received it from you. And R1 will also send the acknowledgement back to R2. So let's now take a look at this in action. I'm going to start by simply building this network that I just described. I have already configured layer 2 part of it, so I do have the connectivity between R1 and R2. So let's just go ahead and confirm that. On R1, I'm going to say show IP route connected, and what I'm looking for here is the network 192.168.12.1. And I do have this network. Actually 192.168.12.0, but I do have the locally attached interface there as well. So I can ping router 2, and on R2, show IP route connected shows me again that I do have my 12 network there, and I can ping R1. So let's go ahead and configure EIGRP here. I'm going to do a very simple configuration of EIGRP. So I'm going to say router EIGRP 12 here, and I'm going to say network 192.168.12.0. I'm not yet going to advertise the loopback interface, because what I want to do is I want to actually start my Wireshark capture and get these update and acknowledgement packets as they are going along, so that I can show you how they actually look. And on R2, what I'm going to do now is I'm going to say router EIGRP 12 network 192.168.12.0. So at this moment, I can go ahead and start my Wireshark capture here, and I'm just going to capture this on Ethernet 1 interface here, and what I'm interested in seeing are only EIGRP packets. And I can see here that the hellos are being sent from time to time. Let's go back and add that loopback interface to our EIGRP. And I'm obviously going to do that on R1. So I'm simply going to repeat this command here, and I'm just going to make sure that I add the loopback interface here, and I'm quickly going to switch. When I press enter here, I'm quickly going to switch to my Wireshark, and now I'm going to stop the capture so that I can explore what was happening here. Now, what I'm looking for here is this update packet here. So I have received the update packet, and I want to observe couple of things here. Now, the first thing that I want to observe is that the source IP address of the packet was obviously R1, and I can see that the destination was 224.00.10. So I can see that this was actually a multicast update. Now, if I open and take a look at what is contained in my EIGRP update packet here, what I'm seeing is obviously that there was an internal route that is being advertised, and I can see here the network of my loopback interface 192.168.0.1/32, and here if I open this field that talks about wide metrics, here I will see information about the reliability, load, delay, bandwidth, and so on, about the things that are actually used to calculate the metric. And I'm going to talk about these metric components later on. So I can see that there was this update packet going out. And as I said, please take note that the destination of this packet was 224.00.10. Now, the next packet here that we are seeing is an actual acknowledgement. And you can see here that Wireshark tells us that this was a hello packet, but it's actually an acknowledgement packet. So this bit here tells us it was an acknowledgement, or actually this bit if we were using Wireshark to analyze this, but I'll show you where in the packet this is actually contained. Now, the more important information here is that the source and destination are that of R2 and R1 respectively. So here we have R2 is sending the packet as unicast to R1. These are no longer multicast packets. So even though the update here was multicast, the confirmation that this was received is sent as unicast. The reason for that is, remember that this is an Ethernet interface. We could have multiple neighbors, and R2 is telling R1, hey, I received this information. There is no need for R2 to tell this to some R17 that might exist on the same subnet. So it just informs R1 about this information. Now, if we go back to our update packet here, there is going to be a field called sequence, and we can see here that sequence was 3. What is the sequence number going to be? It's not really relevant, but what is important that in our acknowledgement packet here, we're going to have the acknowledge field with the same number 3. So this here tells us that, look, I am acknowledging right now I'm acknowledging the arrival. I'm acknowledging that I have received the update that carried the sequence number 3. Now, another thing that I mentioned before is that we can see that R2 here is actually going to update as well. It's going to send the information about this same route. We can see that this is the same route we are talking about. Actually, not that one, that's the route already. It's this one here. We can see that the same route is being sent, and we can see here that the delay has been set to infinity. So we are basically advertising the route back to R1, and we can see that R1 is actually going to confirm, yep, I have received this information. I'm not going to do anything with it, but I have received it. So in a nutshell, this is how the routes are exchanged between two neighbors. Let's now talk a little bit about EIGRP metrics. The reason why I have an empty slide behind me is that I would like to start this part of this session with a little bit of a warning. That warning is really that what I'm about to say is not necessarily in line with official Cisco documentation, or for that matter, Cisco Press books. There are many misconceptions when it comes to EIGRP metric. The first thing that you are going to hear is people talking about EIGRP metric. This is not necessarily correct. EIGRP has multiple metrics, and what makes up those multiple metrics is also a matter of a debate. Allow me to explain that to some degree. The first thing that I would like to mention is that when you look at the output of certain commands that I'm going to show you in iOS, like for example, show IP EIGRP topology, you're going to see the mention of this concept of this term vector metric. Now, vector metric is simply the list of all metric-related information that is communicated and maintained between the neighbors and in their topology tables. What constitutes vector metric are bandwidth, and only the lowest value of the bandwidth on the entire path is going to be carried along. Delay, which is the cumulative value of all the delays configured on the interfaces along the path. Reliability, and here we are again keeping just the lowest value on the path. Load, and the highest value is kept. Now, the next two are what is a matter of debate. Some people consider these to be part of the metric, some don't. I personally do consider them to be part of the metric, part of the vector metric, and they are MTU, where only the lowest value is carried, and the hop count, which is the cumulative value, and it by default has maximum value of 100. Which means that if we receive the route that has a hop count of say 101, the local router won't use it. It's sort of a last resort loop prevention mechanism. Now, there could be some other reserved values that might be used in the future by EIGRP, so there is a possibility of seeing that in output of some commands, or indeed when you do capture of updates on your interfaces using say Wireshark. Of those values, some values are going to be used to calculate the composite metric using the metric formula. Those values that are going to be used are bandwidth, delay, reliability, and load, and by default only bandwidth and delay are going to be used. Reliability and load are not used. These values are then used in conjunction with the so-called K values, and there are 5 K values, and depending on the iOS version you might actually see K number 6 as well, which is going to be used with those other reserved metrics in some applications that really have nothing to do with routing of IP traffic. They have to do with something else. And these 5 K values, by default, K value 1 and K value 3 are those that are going to have non-zero value. And these are the values that are used to modify bandwidth and delay in some way. K values 2, 4, 5, and 6 for that matter have value 0. So how is this used together with our metric formula? So let's take a look at the metric formula. Wow, this is fun. Now, what I want you to look at here is not something that you can probably or possibly remember. This is a very involved formula. So let's take a look at the important bits. The important bits here are that there is a certain K value number 1, and we can see that the default here is to have it a non-zero value that is related to bandwidth. So we can say that the K value 1 controls how bandwidth will be used to calculate the metric. Then we can see here K value 2, which is again used with the bandwidth, but really what figures here is load. So we can say that K value 2 is used to control how we use load information in calculating our metric. Then we can see a very straightforward relationship between K value 3 and delay. So we can say that K3 here controls the delay. And remember, K1 and K3 are those that are by default set to 1. The others are not going to be used. And then we have K values 5 and 4. So 4 and 5 are actually going to be used to control reliability as part of our metric. Now, no one really expects you to know this formula, to know how to calculate the metrics manually, but it's a good thing to understand how this process actually works internally in iOS. One thing that I would like you to pay very close attention here is that MTU, hop count, and other reserved values by default do not figure in this metric formula here. So MTU, even though it's communicated as part of the vector metric, it's not going to be used when calculating the composite metric. And composite metric is the value that ends up inserted into the routing table. This is what is going to be used to calculate the best paths, to insert them in a routing table, or to find the alternate paths, the whatever they might be. So the composite metric is what is actually used to make routing decisions. But in some cases, and some relatively obscure cases, the MTU value can be used as a tiebreaker information. If we have multiple routes that say have equal cost, and we are exceeding the number of routes that can be inserted by EIGRP into into the routing table, we need to make a decision which routes to use, which one of those many routes we are going to use. And MTU comes into play here. Those routes with the highest MTU will be inserted first, and then simply then other routes are going to be inserted by their age of arrival. So the youngest routes are actually not going to be used. If they all have the same MTU, then just the age will be used. And as I said, the hop count is going to be used only as the last resort loop prevention mechanism. So let me present you this same information in slightly different way so that you can maybe see the relationship between these metrics. So we have now learned that EIGRP has bandwidth, delay, reliability, load, MTU, and hop count as parts of what I like to call, or what EIGRP calls, vector metric. So this is the information that is always going to be communicated to the neighbor. So all these 6 values will be communicated to the neighbors. Based on the values of these 4, so bandwidth, delay, reliability, and load, we are going to calculate the composite metric. So composite metric is going to be calculated using these 4 values. But these 4 values are not born equal. Bandwidth and delay are, first of all, used by default, so we can say that they are used by default, but also they are something that, and this is my term, I like to call hard metrics. And reliability and load are something that I like to call soft metrics. Now, why do I call them hard metrics and soft metrics? Any change in hard metric, that means whenever we change the bandwidth or delay associated with a particular interface, the change of these values is going to trigger what is called a reconvergence event. Reconvergence event simply means that the router, as the result of changing these values, is actually going to advertise the route associated with this interface. However, change in soft metrics, that means if reliability or load change on an interface, does not itself trigger a reconvergence event. So if the reconvergence event was triggered by change of hard metrics, the snapshot value of reliability and load would be taken at the time of the convergence event and used to advertise the routes. Now, mind you, reconvergence event is also interface coming up or interface going down. That is also a reconvergence event. Now, MTU, as we learned before, is going to be used as a tiebreaker, and hop count is going to be used as the last resort loop prevention. Hop count can also be used for very esoteric, very unusual form of route filtering that we are going to examine a little bit later on. How can it be used? Let's say that we have a network in which we expect the routes to be only, say, 2 or 3 hops away. So no matter where the routes are coming from, let's not accept routes that have more than 4 hops. In that case, we could configure our router to reject all the routes that have 4 or more hops. And in that case, hop count is not only going to be used as a loop prevention mechanism, which it is what it's designed to do, but it's going to be used as a filtering mechanism. Not a very efficient or very scalable or very flexible one, but it can be used as a filtering mechanism. Now that we know what makes up EIGRP metric, let's take a look at how this information propagates throughout our network. So let's say that we had a network consisting of, say, 4 routers, and I'm going to call them R1, R2, R3, and R4. And let's say that here behind our router R4 we had some network, let's call it network N, that we wanted to advertise using EIGRP throughout our network in this direction here. Now, as this information goes from R4 to R3 to R2 to R1, each of the routers is going to modify the vector metric in some aspects and then communicate that information to its neighbor. Now, to examine this, I'm going to give all of these interfaces on my routers some identifiers, some names, so that it becomes easier to understand how this information propagates. So let's say that on R4, this interface here is interface 1, this is interface 2, 3, 4, 5, 6, and 7. Now, each and every one of these interfaces will have associated value of bandwidth, associated value of delay, reliability, load, and MTU. Now, hop count is not associated with any interface in particular. It's simply going to be increasing from R4 to R3 to R2 to R1. So that information is simple enough to understand. Now, when R4 injects this route into EIGRP, it's obviously going to use the information associated with this interface. That means interface associated with bandwidth associated with interface 1, delay, reliability, load, and whatever the MTU was. Now, remember before I proceed that for bandwidth, at the end we are going to be seeing only the lowest value of the bandwidth. For delay, we are going to be seeing the cumulative value. For reliability, we are going to be seeing the lowest value. For load, we are going to be seeing the highest value. And for MTU, we are going to be seeing the lowest value. For hop count, it's also going to be cumulative value here. So when R4 advertises this information now out towards R3, important thing to understand is that this interface 2 will not figure in any way in propagation of the metric. What R3 will do when it receives this information here, when it receives this information from R4, it's going to take a look what is the information that it has received. So all of this information as it was received from R4 to R3, and then it's going to modify these metrics as they are received according to whatever the configuration on interface 3 is. So we can say that so far interfaces 1 and 3 have participated in calculating the metric. Similarly, when R3 advertises this information to R2, interface 4 will not figure in this communication. What will figure is the configuration on interface 5. And again, when R2 communicates this information to R1, whatever was configured on R6 is irrelevant. What is configured on R7 here is relevant. So we can say that interfaces 1, 3, 5, and 7 will be the ones that are going to be taken into account at all to calculate final metric as this route is being advertised from R4 to R3 to R2 and finally to our R1. At this point you might be asking yourself, why is this so? Why are these interfaces here, 2, 4, and 6, not used in calculating the metric? Well, think about it. When the routing information is communicated in this direction, that is done for the purpose of sending the actual traffic in this direction. So if R1 has the traffic to send, is information on R6 in any way relevant to R1, or is it the information on R7 that is actually relevant? Same thing goes for R2, same thing goes for R3, and finally same thing goes for R4. We don't care what is some fictional cost on devices on network end. We care about what is our own cost, what is our own metric to actually send this traffic out of this interface. The time has come now to talk about EIGRP topology database and the best path selection. But as you are probably used to by now, before I can do that, I have to talk about one other thing. And that other thing is a specific EIGRP terminology, specific names for certain things that EIGRP is using that pretty much no other routing protocol does. What are these terms? The first one is a successor. Sometimes this is referred to as simple as. Successor is EIGRP's name for the best route to reach a particular network prefix. So let's say that, for example, we have a network prefix of 192.168.0.0/16 and we have two paths to reach it. And let's say that this is the best path and this is the second best path. This path here simply is called a successor. Feasible successor is a loop-free alternate route, And keep in mind that we could have multiple alternate routes that are loop-free. And how EIGRP determines whether they are loop-free or not comes at the very end there with a feasibility condition test. But feasible successor is going to be the best route that is considered to be a loop-free alternate. Distance is EIGRP's name for a calculated composite metric. Feasible distance is simply a successor's distance. So let's try to get to the bottom of this. Feasible distance, successor's distance. So feasible distance is simply the calculated composite metric of the best route to reach a particular prefix. Advertised distance, sometimes also called reported distance or AD or RD, is a calculated composite metric based on neighbors' vector metric values. I'll explain this in just a second. A feasibility condition is simply a simple check to determine do we have a loop-free route. And this simple check is the reported distance the calculated composite metric of the neighbor's vector metric, is this value lower than our own best route? Is it lower than the feasible distance? So let's take a look at these couple of more confusing ones in some more detail. For that, we are going to use the exact same network that we used in the previous example. Now, let's take a look when R4 generates its routing update and it sends this information to R3. We know that it's going to list a particular vector metric in this update. And we know that R3, when it receives this update, it is going to use its own local parameters to calculate its own distance. Now, before R3 does that, it is actually going to take this these values, this vector metric, it's going to use the bandwidth, delay, reliability, and load from this update from R4, and it's going to calculate what we call the reported distance. Now remember that this is sometimes called the advertised distance, but I prefer calling it reported distance because if I use AD, it associates me too much with the administrative distance, which is completely unrelated term. So now that R3 has calculated reported distance from R4, what it's going to do, it's going to use the parameters from its local interface based on these rules that we have examined here. It's going to create its own successor with a particular distance being the metric. So this is the first thing that happens. Now, what is a feasibility condition? Feasibility condition is going to be a simple check. Let's say now that, for example, R2, for whatever reason, reported that it has reachability with this network N. Let's say that, for example, R1 had the connectivity to it. So now R2 is telling us, hey, you know what? I have this network N, but it's maybe a little bit higher cost than the one received from R4. So what R3 is going to do here, it's going to look in a reported distance from R2. So it's going to calculate the reported distance using the metric formula that we explained earlier based on the parameters that R2 is sending in its own vector metric here. It's going to calculate what is the reported distance, and then it's going to look at its own current successor, and it's simply going to say, is the reported distance here lower than the distance of the successor? Now we know that the distance of the successor is simply called the feasible distance. And this verification here represents what we call a feasibility condition check. But why does it exist in the first place? Well, that's the part of the best path selection algorithm in EIGRP. So let's take a look at that. Now that we learned about the terminology of EIGRP, let's take a look at how this is all used in the topology database and the best path selection process used by EIGRP. When we talk about the protocol database, the EIGRP topology table, so-called, this is the table internal for the router that contains information about all EIGRP routes. And by all, I really mean all. The local routes, the routes that have been locally injected into the EIGRP by that particular router are also going to be in the EIGRP topology table. so are going to be the routes that are learned from all of our neighbors. It is this table here that provides us with the information that we can use to determine which routes are the best routes and need to go into the routing table. This decision, which routes need to go into the routing table in EIGRP, can be made locally by the router, and here on the slide behind me I have it as a local decision. Now this decision can be very simple, or it can be a little bit complicated. Now, not really complicated, but it could be a little bit involved. So the simple decision is if we are for the first time hearing about a particular route. Now what I mean by first time is the decision that needs to be made is not a result of this route disappearing from the routing table and us needing to find a replacement route for it. But this is the first time that the route showed up. We had no prior knowledge of this particular route. In that case, the decision is going to be very simple. Let's insert this route into the routing table. But what happens if we learn this route from two different sources? Let's say two upstream routers are giving us information about how to reach a particular network. Again, this is a local decision, and it is going to be made simply based on the distance. Now remember what the distance is. Distance is the calculated composite metric for a particular prefix based on the information from the vector metric. However, if our decision is being made as the result of a particular route being removed from the routing table. So let's say that we had, again, two upstream routers, and one of them is telling us, hey, you know what, no longer use this route, and we had a feasible successor for that route. This is still a local decision, but in this case, the route that we are going to end up using needs to have already passed a feasibility condition test. And remember, the feasibility condition test is the reported distance of the route lower than our feasible distance? And the feasible distance in this case would be the old metric of the route that just disappeared from the routing table. And in some cases, the router cannot make a local decision. It needs to go and find the replacement route in a distributed fashion. And this is the situation when we do have a backup route in our routing table, but unfortunately that route has not passed a feasibility condition. If this is the case, the router cannot guarantee that the backup route, that the second best route it has in the topology table, is loop-free, and in that case it needs to go active on the route. What going active in terms of EIGRP means is that the router needs to go out and ask the neighbor from which it learned this route, is it okay to use this route? This is done using an EIGRP packet, a new message that I mentioned before but I never explained, which is the query message. It's simply going to send out the query to the neighbor, hey, can I use this route? Is this your route? Is this still valid route? Maybe the upstream neighbor also lost its route the same way we lost our primary route to reach a particular prefix. If the upstream neighbor is ready to accept traffic for this destination, that means it's probably a connected route, it is going to respond back with the reply, yes, it's okay, go ahead, use this route, and then we can insert our route into the routing table. Sometimes this going active on a route can result in a very specific situation in EIGRP that is called stuck inactive. What is stuck inactive? Now imagine that we are sending the query to our upstream, but our upstream router doesn't have a local route, or it does have a route learned from someone else. If it receives a query, it needs to send it to the router from which it itself learned that particular route. So we need to wait for a certain period of time until this query goes out and out and out and out and finally reaches the destination in our network, the router that has a connected route and was the original injection point for our route into our EIGRP routing domain. When that happens, it could be that there is some communication problem somewhere between several routers on the path, let's say just between two of them, and for some reason the query either never goes out or we never receive back the response. If that happens and a particular timer called the active timer on the router expires, and by default this is a very, very long time, it is going to be 3 minutes long. If this timer expires, what's going to happen on our local router depends on the iOS version. In the older versions of iOS, what would happen is a very drastic measure. The router would say, I have sent the query to you, you are not sending the reply. I will have no business and dealings with you. And it's going to tear down the relationship. It's going to throw away all the routes, not only the route that is stuck inactive, learned from that particular neighbor. And then it's going to reform the neighborship and relearn some of the routes. But the damage has been done. We have lost all the routes. In a particular version of iOS, and I believe it was around 12.2 or 12.3, long time ago, Cisco recognized this as a potential problem, and it introduced 2 additional messages in EIGRP called stuck inactive query and stuck inactive reply. How they operate is when a particular router has sent a query and it's waiting to receive a reply and it's not getting it, about halfway through the active timer, so about 1.5 minutes after it sent the original query, it is going to send out stuck inactive query. It's going to ask its upstream, hey, are you maybe still waiting on the response yourself? And the upstream neighbor is going to respond, yeah, I'm still waiting for the response myself. So we are okay. There is no reason to tear down this particular neighborship, but let's wait to see what is happening with our upstreams. Now, if the stuck inactive query results in no reply, the router is going to know that the upstream neighbor is experiencing some problems, or there is a problem with the communication between them. So instead of waiting for 3 minutes to destroy the relationship, which is, by the way, broken to begin with, it is going to do it after about 1.5 minutes. If it receives stuck inactive reply, on the other hand, it's just going to keep on waiting until the active timer expires, and when the active timer expires, it's simply going to throw away the route it already learned. I understand that this is, or might be, a little bit too much to digest. So let's take a look at a couple of examples of how these things may work. So what I'm going to do here is I'm just going to set up a sample network, and I'm just going to use 3 routers. And they're going to be my routers 3, my router 4, and router 5. Now I want to use 3, 4, and 5 because I have used 1 and 2 in the previous example, and I just don't want to start reconfiguring everything from scratch. And let's say that these 2 routers, 4 and 5, have a common shared network here on their gigabit interfaces 1. And this network is going to be 10.0.0.0/24. And between 3 and 4, I'm going to have, this is going to be interface gigabit 2. On 2 sides, this is going to be gigabit 3, and let's say that this is going to be 192.168.35.0/24, and this is going to be 192.168.34.0/24. And what I want to do here is I want to run EIGRP, say process 345 between them. And I will configure it using the simplest method, and that is going to be the numbered mode. So let's start configuring this, and let's see what is going to be the end result. And we are going to focus only on observing what is happening on R3. R4 and R5 here are just route feeders, so to speak. And we are going to be looking at this one route and the behavior associated with it. The first thing that I'm going to do, as always, is going to be the verification of the connectivity. So I want to make sure that my R3, 4, and 5 can actually communicate. So I'm going to go to R3 and I'm going to say show IP route connected, and I just want to make sure that I can communicate with both R4, which I can, and with my router 5, which I can here. On R4, I'm going to say show IP route connected. I'm going to make sure that I can communicate with R5 and that I can communicate with my router 3, which I can, and on R5 I'm going to do the same thing. I can communicate with R4 here and 192.168.35.3, so I have the reachability as expected. So let's configure EIGRP here. Now this network 10 between my 4 and 5, I don't really need to have a neighborship here. So what I'm going to do here on 4 and 5, I'm going to declare this interface gigabit 1 as passive. I just need these routes injected. I don't actually need the connectivity there. So let's start with R3. And the configuration on router 3 will be very, very simple. I'm just going to say router EIGRP 345, and I'm going to say network 192.168.0.0. And I'm going to use /16 wildcard mask here because that will cover both of my interfaces. So if I do show IP EIGRP interfaces, this is what I'm going to be seeing, that both interfaces gigabit 2 and gigabit 3 have been enabled for EIGRP. Now, before I continue configuring stuff on 4 and 5, let's take a look what is the situation now on R3. Now that I already have EIGRP running, even without any neighbors, I should have the EIGRP topology table, and I can take a look at it. If I do show IP EIGRP topology, what I'm going to see here is that in my topology table, I actually do have two networks. I can see 192.168.34 and I can see 192.168.35.0/24, and I can see that both of these are in the topology table with one successor. That means that I only have one path to them, and I can see that the calculated metric for them is 2816. Now, what I can also see is that these networks here are passive. And remember, in EIGRP, passive means good. Active means that we are actively looking for a replacement route. Also, I can see here that I can have the query is in process, or that we are receiving the reply that we are replying ourselves, or that we are stuck in active situation. But these are very, very transient states. So what you are mostly going to be seeing with your EIGRP routes are either passive or active states. So it's very, very important to understand how to read this. One more thing that I would like to show you before I continue configuring is show IP EIGRP topology 192.168, let's say 34.0/24. This is a little bit expanded view of what I'm going to have. Now, what is this going to show me is the actual entry in the topology table. So this information here just shows me a little bit summarized information. It shows me the summary of the topology table information for these prefixes. But with this longer output here, I can see what is the actual vector metric here, and I can see the minimum bandwidth, the total cumulative delay. I can see what is the reliability, what is the load, what is the minimum MTU. I can see the hop count, and I can see what is the router that actually injected this route. And I can see that this is a local router because this is my own IP address. Also, what I can see here, and this is very, very significant, I can see the calculated composite metric. And this value here consists of actually two values. So we have our own distance, or in this case it will be feasible distance, but I'm just going to use D here, / reported distance. So this value after the slash is reported distance. For the local route, there is no reported distance, so obviously the reported distance here will be 0. And distance, and in our case this would be a feasible distance because this is the actual successor here. This is showing us the calculated metric for the EIGRP route. And this is the same value that we have seen in this summarized output. We can see here that it's the same feasible distance from the local perspective. So this is the view of the topology table on R3 before we have actually enabled any other routers for EIGRP. So let's go ahead and do that. What I'm going to do here now is I'm going to go to R4 and pretty much repeat the configuration. I'm going to say router EIGRP 345, and instead of just doing network 192.168 as I did on R3, I'm going to say network 0000, which is going to enable EIGRP on all the interfaces. But before I do that, remember that I wanted to create gigabit interface 1 as a passive interface. So I'm just going to declare it as passive, and I'm going to say network 0000. Now I should see that the neighbor with R3 came up, and let's configure R5 in the exact same fashion. So router EIGRP 345, passive interface gigabit 1, and network 0000. And again, I can see that with R3, I have the neighbor, but there is no neighborship coming up between 4 and 5. And this is exactly what I wanted to see. Now, let's take a look what this did on R3. If I do show IP route EIGRP, now I'm going to see that I do have network 10 as an EIGRP route. So remember that D here stands for EIGRP. I'm going to see this route available or reachable through true destinations. So EIGRP by default is going to implement or do something that we call ECNP, or equal cost multipath. Now I can see that these two prefixes, or this one prefix, these two paths for this one prefix have the exact same calculated metric. They have the exact same distance. Now, let's take a look at this same information in the EIGRP topology table. So if I do show IP EIGRP topology now, what I'm going to see here is that I do have two successors. So these are equal cost routes, and I can see here that this here is my feasible distance, and I can see here the reported distance, and I can see that the reported distance in both cases was the same. Given that all links in my network share the exact same characteristics, they are all gigabit interface, gigabit Ethernet interfaces, this is no surprise that I'm going to end up with a situation like this. And if I take a look at a little bit more details about this route, what I'm going to see here is that I have pretty much identical information. I can see that the same bandwidth was reported, I can see that the same delay was reported, the same reliability load, etc., etc., etc. But keep in mind that we only care by default about the delay and the bandwidth. If we wanted to use reliability and load, we would have to modify which K values are in use. So let me just briefly show you that piece of configuration. So router EIGRP 345, if we wanted to modify our K values, we would have to use the command metric weights. Now, this is from the old times when EIGRP was supposed to have different kind of routing topologies depending on which TOS values in IP packets we had. That was never implemented, so TOS 0 is the only one supported. But anyways, we still have to use metric weights 0, and only then we have to specify K values. And remember that the default is 10100, and if I press enter here, nothing is going to change because this is the exact default configuration. So if I take a look at the router EIGRP, I see that this didn't even end up in the running config. But if I change the metric weights, for example, now I'm introducing K5 into the mix, I will see not only that my neighbors went down, but my neighbors are not re-establishing. Because remember, we talked about this, that K values are part of the verification process during the formation of the neighbors. And if the K values are mismatched, we are not going to have successful neighborship. So let's fix this and go back looking at our topology table. So again, at this point, I have these two paths to the same prefix in my topology table and in my routing table. But let's change things a little bit. Let's modify the metrics on one of the links, let's say between 3 and 5, and see how that is going to affect our routing table and our topology table. The first thing that I'm going to do is I'm going to increase the delay on the interface between routers R3 and R5. That means on gigabit 3 on R3. But before I do that, how much should I increase the delay by? What is the current value of delay? Well, to do that, I'm just going to go to R3 and I'm going to say show interface gigabit 3. And by running this command, I'm going to see what is the current value of delay. And I can see that it is currently set to 10 microseconds. So if I increase it by any number, I should have some change in the perceived cost, in the perceived metric, the distance, call it whatever, on R3 for our 10.0.0.0/24 route. So I'm going to go to interface gigabit 3 and I'm going to say here delay, and I can see that the value is specified in tenths of microseconds. So I'm just going to increase it by a little bit. Let's say I'm going to set it to 10,000 microseconds. Now I did specify 1000 here, but remember this is in tenths of microseconds, so this is actually 10 times the value that we already have, and we can see here that that is the actual value that we end up having, 10,000 microseconds. So now if I on R3 do show IP route EIGRP, I still see that I have the route to 10.0.0.0, but this time it is only through gigabit 2, which is through our router 4. Where did our route go towards router R5? Well, it disappeared from the routing table because now the metrics are different. Let's take a look at the topology table. So if I do show IP EIGRP topology, what I'm going to see here now is again that for 10.0.0.0/24 I do have two routes. Now take a look at this. Both of these routes have the same reported distance. So remember, this value here after the slash is the reported distance. But when we have added our local values, we can see a clear difference in calculated distance. So this here becomes our successor. But is this route here our feasible successor? How can we know that? Well, we can know by just looking at this output. What we need to ask ourselves, is this value, the reported distance of the second best route, lower than this value here? Remember, this here is feasible distance and this here is reported distance. And what is a feasibility condition? Feasibility condition is the reported distance lower than the feasible distance of the route? And in this case here, we can determine that yes, we do have a feasible successor. Let's try to confirm that. So if I run show IP EIGRP topology, and let's say I run detail links here, this doesn't give me any additional information. So what other command could I run? Well, I can obviously run 10.0.0.0/24 here in the output, and again, I don't see here very clearly do I have a feasible successor or not. So the only way to actually find out do you have a feasible successor is to calculate yourself, to look at these values, to look at what is the feasible distance and what is the reported distance of other routes, and in that case you are going to determine that we do actually have a feasible successor. So how does feasible successor actually help us? Well, to do that, what I'm going to do now is I'm going to bring into my analysis my Wireshark. How is Wireshark going to help me determine that? Well, the first thing that I want to do here is I want to see what is going to happen if R4 suddenly stopped advertising this interface. So I'm going to go on R4 and I'm going to shut this interface down. And then I'm going to observe what is going to be happening on the communication between R3 and R5. What I'm expecting to see here, because R5's route, this one that we received here, is a feasible successor. I don't expect to see any additional communication between R3 and R5. Now, what I mean by additional communication, I don't expect to see router 3 going active on this route towards R5. Let's take a look. So I'm going to go here and I'm going to go to R4 and I'm going to go to interface gigabit 1 and I'm going to prepare it for shutdown. I'm not going to shut it down yet, and then I'm going to go to my Wireshark and I'm going to start capturing all EIGRP packets that are happening on gigabit interface 3. So I should be seeing some hellos there. So this is what I'm seeing. So let's now go back here, shut this interface down, and let's go here and see what is that we observed. Now, the only thing that we have seen here is an update. Now, we are obviously going to have an update sent out because something has changed. Now we are suddenly using this different route, and I wouldn't be surprised here if we open this up. What we are going to see is that this route here was actually R5's route, and we can see here based on the router ID. So what has happened here is we had router 4, router 3, and router 5. Remember, both of them were advertising this 10 network. So when R4 stopped advertising, R3 promoted the feasible successor into the routing table and immediately notified R5 about the change. But it also means that it's going to advertise R5's own route back. And we have seen this before when we first looked at the updates. But the important thing here that we need to observe is the complete absence of router 3 doing anything with router 5, meaning that we didn't go active on the route and that the feasible successor was promoted. Now, at this moment, you have to take my word for it. Let's go back on R3 and see what has happened on R3. If I do show IP route EIGRP, here is my route from R5. I can see it here. It's installed in the routing table. And it was promoted because it was a feasible successor. But let's see what is going to happen if, let's say, the backup route that R3 received from R5 was not a feasible successor. And that's much more easily done than you might think. The first thing that we are going to do is I'm going to go to R4 and I'm going to make sure that the situation is as it used to be before I made any changes. So I'm going to go to gigabit 3 here and interface gigabit 3, and I'm going to say default delay. So at this moment on R3, if I do show IP route EIGRP, I should be seeing 2 routes in the routing table, just like I did before the change. And now I'm going to go to R5, and on R5 on interface gigabit 1, here I'm going to increase delay significantly. Now what this is going to cause, and let me try to show you that, what this is going to cause on R5 is that when R5 advertises this prefix to R3, this reported distance here is now going to be higher than the actual feasible distance that R3 has, because I have modified the metric on this interface here. So if reported distance is higher than the feasible distance, we know that we don't have feasibility condition, that the feasibility condition here is not going to succeed. Let's go ahead and confirm that. So if I go back to R3 now, if I do show IP route EIGRP, as we might expect, we are seeing only one route in the routing table. Let's take a look at the EIGRP topology table. So if I do show EIGRP topology, this might surprise you a little bit now. I'm going to see in this output only a single path. Now, where is the path through R5? It used to be here before, but now it's not here. Now, this is one very, very important bit of information. Remember in the previous example when I told you that the only way to figure out that you do have a feasible successor is to actually look at these metrics and calculate them and so on. That's not actually true. The presence of this second route here, the one that we used to have here before with the higher, with the higher distance, but the same reported distance here, that was an indicator that that second route was a feasible successor. Now, the absence of it here doesn't mean that we don't have it in the topology table. It simply means it's not a feasible successor. So how can we know for a fact that we actually do have it in the topology table? Well, we have to run a slightly different command. We have to run show IP EIGRP topology all links. Now, with this output, we are going to see both of these routes, both of these paths here. And now we can clearly see that the reported distance is much, much higher than our feasible distance. Therefore, this route here is not going to be considered to be a feasible successor. So what is going to happen now if I was to shut down the interface on R4? Let's find out. Again, I'm going to go back to my Wireshark and I'm going to restart the capture. So I'm seeing the EIGRP hellos. That's what I'm expecting to see here. So let's go here. Let's shut this down and let's go back to my Wireshark. Now we are seeing slightly different output. The first thing that I would like you to take a look is this. Now we did have a query. We can see that it was R3 here that sent the query to 2240010, and this was a query. So let's take a look at this packet here. So I already have the EIGRP expanded here. What we are looking for here is we are sending the query for this particular route here. So we are sending this route and we are saying, okay, I have lost the route from R4 that I used to have for this prefix 10000/24 with these particular metrics. Actually, the metrics here are irrelevant. We are simply sending the query for this particular route here. Now, the first thing that we are going to see here is going to be from R5 sent directly to R3 is going to be an acknowledgement. It is going to be an information that R5 has actually received the query. It's not responding, it's just saying, I got it. The next thing that we are going to see here is going to be the reply. Now, R5 is telling R4, you know what? I actually do have this route available. This is okay. And then the next thing that we are going to see is that R3 received this route. So this is the message from R3 to R5 where it acknowledges that it actually received this information. And at this point, R3 started installing this in a routing table. And finally, then we have that reverse update, that poisoning update here that was sent from R3 to R5, or actually to 2240010 with an update with R5's own route, just like we observed before. But the important part here was this query here and this reply. This is the significant difference. This was an example of the router going active on the route. So if we go back to our terminal on R3 and if we take a look at show IP route EIGRP, now we are going to see that the route from R5 has been successfully installed. Let's clean things up. So I'm going to go to R5 and I'm going to say default delay, and I'm going to go to R4 here and I'm going to say no shutdown. So I wanted to have my pristine state, and now if I do show IP route EIGRP, I should be getting the second route. There it is. It took a couple of seconds. So now I have the situation as it used to be. So let's talk a little bit about load balancing or load sharing in EIGRP. What we have here right now is, as I said before, something that is called equal cost multipath, or the load balancing across multiple paths that share the same cost. EIGRP is the protocol that supports unequal cost load sharing. It allows us to load balance over two paths that don't have the same cost. Now, what are the prerequisites for unequal cost load balancing? Well, there is only one. All candidate routes that need to become eligible for unequal cost load balancing need to pass a feasibility condition. So if the routes have not passed a feasibility condition, they cannot be load balanced. So let's put this network scenario in a condition where we have only one route in a routing table, but the second route has actually passed a feasibility condition. Remember how we did that first. So I'm going to go now to interface gigabit 3 and I'm going to say delay, let's say 1000 here. So if I do show IP route EIGRP, I'm going to see that I have one route in a routing table, but if I do show IP EIGRP topology, I'm going to see that there is actually a feasible successor here. Now we can see that the local cost is a little bit higher. So how can I make my router load balanced unequally across these two paths? Well, this is where a special command called variance comes into play. Now, with variance, what we are going to do is we are going to tell our EIGRP router to multiply our feasible distance by a certain number, and all routes that have passed a feasibility condition that are potential feasible successors, all those routes that have cost, that have the calculated metric, that they have their own distance that is lower or equal than variance multiplied by feasible distance are going to be installed in the routing table. So what I need to do here is multiply 3072 by some number to get the value that is lower or higher than this value here. And by the look of it, this is going to be rather high difference. So what I'm going to do now is I'm going to go actually, you know what? I'm going to do something else. Give me just 1 second. What I'm going to do now is I'm going to fire up my calculator, and I'm just going to say 258816 divided by 3072, and I'm getting the value of 84.25. So the variance that I need for this particular situation, mind you, the difference in metric here is significant, is roughly 85. So what I'm going to do now is I'm going to go to router EIGRP 345, and I'm going to specify the variance, and the possible values for variance are between 1 and 128, and I'm going to specify it as 85. So now what's going to happen is I'm going to get a little bit of a warning message, because there is a really significant difference in metrics here. I used too much delay there. So if I do show IP route EIGRP, now I'm going to see that I have both of these routes here installed in the routing table. But how is the traffic being load balanced there? Well, if I take a look at the output of this command, show IP route without EIGRP here, what I'm going to see here is that the traffic share count here is 80 to 1. So this is now being load balanced in an unequal fashion. That means that roughly 80 times the traffic is going to be sent over this path than it is going to be sent over this path. Because we remember that our difference in our difference in ratio was roughly 85 to 1, but there was that one warning message. Let's make this ratio a little smaller. So what I'm going to do now is I'm going to go to interface gigabit 3, and instead of specifying such a big delay here, let me make it a little bit smaller. I'm still going to have the same thing now. If I do show IP route EIGRP, now I'm going to see that I have the difference in metrics, and now it's significantly smaller. So I don't have to use such a large variance anymore. I can use variance 2 in this particular situation here. So if I do show IP route, actually I do have it in history here. Now I can see that the load balancing ratio, the traffic share count, is a weird difference, weird relationship in metrics here. But this is okay. This is iOS calculating what is the best way to perform an unequal cost load sharing between these two paths. So the significance here is that we can load share over these two paths with an unequal metric, with an unequal costs, but what we need to do is we need to use that variance command. There is one more thing that I would like to show you. So if we do show IP route EIGRP here now, we can see that we are performing unequal cost load balancing between two paths. If I do show IP route 10.0.0.255.255.255.0, I can see what I've seen just before is that we are performing load sharing in this ratio here. It is possible to configure EIGRP in such a way to use only the primary path here and not to use any information, to not send any traffic down the backup path while still having it actually inserted into the routing table. You might be thinking to yourself, what would be the point of this configuration? Well, in some cases it can speed up the convergence by a couple of milliseconds should the primary route fail. And in some high performance environments, this might actually be very, very significant. Luckily, this configuration is very straightforward. So I'm going to go to router EIGRP 345 and I'm going to say traffic share here, and I have two options: balanced, which is the default, which is what we have now, or I can say minimum across interfaces. With this one change now, what I have done is I have changed the behavior of my load sharing. Now I can see that the traffic share count is 1 to 0. Now, this path here is going to be used to send the traffic, and this one here won't, but we still have it in the routing table. If I do show IP route EIGRP based on this output here, we would have no idea that this path here is actually not used to send any traffic.